All right, welcome. Today, we're going to crack the code on a topic that sounds, kind of heavy, higher order differential equations. But here's the secret. These things are basically the language of the universe. They describe everything from how a guitar string vibrates to how electricity flows. So we're going to break them down and show you there's a really simple, super powerful toolkit for solving them.
Okay, let's dive right in. Here's our game plan. First, we'll talk about a key property called superposition. Then, we'll see why our solutions need to be independent. After that, I'll show you a clever little tool to test for that independence, and finally, we'll put it all together to solve a huge class of these equations.
So, first up, superposition. Let's meet our main character for today, the second-order linear homogeneous differential equation.
Now, this is our starting point. The big takeaway here is the word homogeneous, which is just a fancy way of saying the whole thing equals zero. And that simple fact, that it's equal to zero, gives these equations some really amazing properties.
And here is its first superpower, the superposition principle. What this means is, if you can just find a couple of solutions that work, you can mix and match them, multiply them by any members you want, add them together, and you have just created an infinite family of new solutions. It's a huge deal.
Let's see this in action. You can literally take e to the 7x, plug it into the equation for y, and you'll see it all cancels out to 0. It works. Then you do the same thing for e to the 2x, and it also works. So because they both work, superposition tells us that any combination of them is our general solution. Pretty cool, right?
Okay, so superposition is awesome, but it does bring up a pretty important question about which solutions we should actually be using.
And the answer, maybe surprisingly, is no. You can't just grab any two solutions. To build every possible answer to the equation, your solutions have to be, well, fundamentally different from each other. We call this being linearly independent.
Think about it like you're giving directions. You need two truly different instructions, like go 1 block north and go 1 block east. If your directions were go 1 block north and go 2 blocks north, you're not really adding any new information, are you? You're just stuck moving along the same line. It's the exact same idea for our solutions.
So, what we're really searching for is this fundamental set. It's like the perfect team of two linearly independent solutions. Once we find this set, we can describe every single possible outcome of the equation just by combining those two.
But how can we be sure our solutions are actually independent without just, graphing them and eyeballing it? We need a real mathematical tool for this.
And that tool is the Wronskian. Seriously, think of it like an independence detector for functions. We just feed our two solutions into it. It does this quick little calculation with their derivatives, and the result tells us with 100% certainty if they're a good team or not.
Watch this. For that dependent pair, we talked about x and 2x. Let's plug them in. It's the first function, x, times the derivative of the second, which is 2. Then subtract the second function, 2x, times the derivative of the first, which is 1. So we get 2x minus 2x, which is exactly 0.
But now look at our solutions from the first example, e to the 7x and e to the 2x. When you run them through the Wronskian, you get something that is clearly not 0. And that's a signal. 0 means they're dependent, basically telling you the same thing. Non-zero means they're independent, and you found your fundamental set.
And what's even cooler is that thanks to something called Abel's theorem, you only have to check the Wronskian at one single easy point. Pick x equals 0, for instance. If it's not 0 there, it's not 0 anywhere. It makes our job so much easier.
Okay, so we've built our toolkit, we have superposition, we know we need independence, and we have the Wronskian to check for it. Now for the payoff. Let's crack the code for the most common type of these equations.
The secret here is it's absolutely brilliant. We're going to transform this entire scary-looking differential equation into a simple algebra problem you did in high school, a quadratic equation. It's called the characteristic equation, and the roots of this simple equation tell us literally everything we need to know.
So, case 1. If that quadratic equation gives you two different real numbers as roots, let's call them r1 and r2, then boom, your fundamental set is just e to the r1 times x and e to the r2 times x. Done.
For example, this equation turns into r squared minus 3r plus 2 equals 0. You can see right away the roots are 1 and 2. So we can immediately, without any more work, write down the general solution. c1 times e to the x plus c2 times e to the 2x. It's that fast. Okay, case 2. What if the roots are the same? We get a repeated root. Well, we've got one solution, e to the rx, but we need a second, independent one. And the trick?
is just beautiful. You just multiply that first solution by x. That's it.
So here, the characteristic equation is r plus 2 squared, which gives us a repeated root of -2. So our fundamental set is e to the minus 2x, and that second independent solution is just x times e to the minus 2x.
And last but not least, case 3. What happens when our quadratic formula gives us a negative under the square root? We get complex roots. But don't panic, this is where things get really cool. These complex roots produce these beautiful oscillating wave solutions with sines and cosines.
Check this out. The roots here are 2 plus or minus I times the square root of 5. The real part, the 2, gives us that exponential term out front. And the imaginary part, the square root of 5, tells us the frequency of the wave inside the sine and cosine. It's like a perfect recipe.
Okay, let's head into our final section and see how this amazing system we've just built can be scaled up to handle even bigger problems.
And this is the best part. This whole system scales perfectly. A fifth-order equation? You'll get a fifth-degree characteristic equation with 5 roots. And the same rules apply. You know, if you get a root of 1 that's repeated 3 times, no problem. Your solutions are e to the x, then x times e to the x, and then x squared times e to the x. You just keep multiplying by x for each repetition. The pattern is it's perfect.
So we have totally mastered the case where the right side of our equation is 0 when there's no external force pushing on the system. Which leads to the obvious next question. What do we do when there is a force? What happens when that right-hand side is not 0? Well, that's a story for another time.